In this video, we'll talk about the inverse trigonometric functions. We'll start with the inverse of sine. The function f of x equals sine of x is not a one-to-one function on its full domain, and so that means that it can't have an inverse, at least not defined on its full domain. However, we can restrict its domain to a smaller interval, an interval over which it is one-to-one and therefore has an inverse. There are many intervals that we can choose. The interval that we pick is negative pi over 2 to positive pi over 2. On this interval, the function is one-to-one. It starts at minus pi over 2 and goes to positive pi over 2. So on the graph, you can see that it is an increasing function on this interval. In particular, it's one-to-one, so it has an inverse. And in fact, we achieve every value of sine on this interval. We have minus 1 all the way up to positive 1, the smallest value of sine up to the largest value of sine. So we see that every value of sine is obtained on this interval, and each one of those values is obtained only once. So we do have a one-to-one function here. So on this interval, the function is invertible. And we call the inverse of this function the inverse sine, or, as it's also known, arcsine. Here we see just the portion of the function that we're looking at on the restricted domain. So the dashed curve here, which is in blue, that's y equals sine of x, but it's just a portion of it. It's just the part of the graph from x equals minus pi over 2 to x equals positive pi over 2. This is where it's one-to-one. This other graph here is the inverse. Notice that this is the reflection of y equals sine of x through the line y equals x. That's how you obtain the graph of an inverse. The inverse of sine of x on this interval is denoted by sine to the negative 1. But this doesn't mean the reciprocal, this means the inverse of sine, the inverse function. Another notation that's used is the arcsine. The domain of the inverse of sine is the interval from minus 1 to 1, and the range is the interval from minus pi over 2 to positive pi over 2. That's because the domain of the inverse function is the range of the original function, and the range of the inverse function is the domain of the original function. Sine, our original function sine of x, is restricted to this domain. Therefore, the range of the inverse is that same interval. Furthermore, the range of sine is the interval from minus 1 to 1. So the domain of the inverse is the interval from minus 1 to 1. Restricting the domain the way that we did allowed us to take a periodic function, which is not one-to-one, and restrict the domain to a much smaller interval where the function was one-to-one. And in this way, we were able to find an inverse for sine. We can do that for cosine as well. So cosine is a periodic function. That means it repeats, so it's definitely not one-to-one on its full domain. Once again, we want to find a restricted domain, and in this case, we pick the interval from 0 to pi. Notice that we can't pick the same interval that we did last time. For sine, we picked the interval from minus pi over 2 to positive pi over 2. That won't work here. Minus pi over 2 is right here, where the graph crosses the x-axis. Positive pi over 2 is right here, where the graph crosses the x-axis again. But notice on this interval, from minus pi over 2 to positive pi over 2, cosine is still not one-to-one. It does not pass the horizontal line test. That means it's not one-to-one there. So we can't pick the same interval for cosine that we did for sine. We have to pick another interval. We can pick any interval where the function is one-to-one. The one that we traditionally pick is the interval from 0 to pi. So that's this interval right here from 0 to pi. on this interval, you can see that the function cosine is 1 to 1. It's actually a decreasing function here. It starts at 1, and then it decreases to -1. So -1 is right here. So we see that we achieve the maximum value, and then all of the values leading to the minimum value. And again, like sine, we achieve them only once. We achieve all values of cosine, but precisely once. So on this interval, the function is 1 to 1, and so it has an inverse. And again, you can see that it passes the horizontal line test here. So it is 1 to 1 and has an inverse, but just on this interval. The inverse of cosine is called inverse cosine, or as it's also known, arc cosine. On the next slide, we can see the graph of cosine and its inverse. So once again, the dashed line, which is blue here, that's y equals cosine of x, but it's just the part of the graph between 0 and pi. This is our restricted domain. So cosine of x is restricted to the domain 0 pi. That's our domain for cosine. So you can see the graph only exists on this interval from 0 to pi. That's our domain. And our range is the set from -1 to 1, just like it always is for cosine. The graph of the inverse is then the reflection of the graph of cosine through the line y equals x. So that's how you end up with this solid curve here. Notice that its domain is the set from -1 to 1. That's because the domain of the inverse is the range of the original function. Similarly, the range of the inverse function is the interval from 0 to pi. That's the domain of our restricted cosine. So our restricted cosine has domain 0 to pi, so that means the range of our inverse cosine is 0 to pi. Because again, the domain and range between a function and its inverse swap. So the domain of cosine becomes the range of inverse cosine, and the range of cosine becomes the domain of inverse cosine. So the domain of inverse cosine is the interval from -1 to 1, which is the range of cosine, and the range of the inverse cosine is from 0 to pi, which is the domain of our restricted cosine. Or rather, it's the restricted domain of our cosine function. We can do something similar for tangent, although it's a bit different for tangent. The function tangent, like sine and cosine, is periodic, so it's certainly not 1 to 1. You can see that it definitely does not pass the horizontal line test. However, we can choose any portion of this graph between any two vertical asymptotes, and that will give us an increasing 1 to 1 function. Normally what we do is we pick the one between -π/2 and +π/2. That's this curve right here. We could actually pick any portion of the curve that's between two vertical asymptotes, but it's traditional to pick the one between -π/2 and +π/2. Now, you can't actually include the endpoints of this interval because that's where the vertical asymptotes are. -π/2 and +π/2 are not in the domain of the function. They're not in the domain of tangent, so certainly not in the restricted domain. So this interval needs to be modified a little bit. We can't include these endpoints, so this should be parentheses instead of brackets. So every possible output of tangent of x is obtained on this interval, this open interval, not the closed interval, but the open interval. Every possible output is obtained on that interval exactly once. So on this interval, the tangent function has an inverse, which of course we call inverse tangent or arctangent. So now we can ask what our function looks like just on this interval, and also what the inverse looks like. So let's go to the next slide. On this slide, we see both of the functions. We see tangent with the restricted domain, that's this dashed curve here. And we see its inverse, which is the reflection through the line y equals x. So that's this solid curve here. Notice that it has horizontal asymptotes. The original function, y equals tangent of x, is between two vertical asymptotes. When you reflect tangent x through the line y equals x, you don't just reflect the curve, you also reflect its asymptotes. So these vertical asymptotes become horizontal asymptotes for the inverse. So the inverse is this curve, this solid curve. The original function, tangent of x, is between minus pi over 2 and positive pi over 2. Similarly, its reflection through the line y equals x is this curve, which is also between minus pi over 2 and positive pi over 2. Only before, tangent was between minus pi over 2 and positive pi over 2 on the x-axis. Now the inverse tangent is between minus pi over 2 and positive pi over 2 on the y-axis. So we have these horizontal asymptotes now. Let's just look at this again in the next slide. This is just the graph of the inverse. This one's a little bit different than the other functions because the other functions had a very small domain, but arctangent or inverse tangent has a very large domain. That's because the range of tangent is the set of all real numbers. So the domain of this inverse tangent is the set of all real numbers. So the domain is the set of all real numbers. Its range is the open interval from minus pi over 2 to positive pi over 2. Again, not including the endpoints. That's because that's the domain of the inverse, or that's the domain of the original function. Now again, we put brackets here, but these should be parentheses. Minus pi over 2 and positive pi over 2 are not in the domain of the original function, so they can't be in the domain of the restriction. We have to look at some small interval where tangent is defined. And that interval that we pick is the open interval from minus pi over 2 to positive pi over 2. That's the domain of tangent. So the inverse of tangent has range the same interval from minus pi over 2 to positive pi over 2. And again, it's the open interval. In terms of the graph, you can see that it never actually attains positive pi over 2. It gets closer and closer, but it never actually gets there. The same is true of minus pi over 2. As x goes left, you get closer and closer to y equals minus pi over 2. But you never actually get there. So there are no output values actually equal to pi over 2 or minus pi over 2. That's why you have an open interval, not a closed interval. Let's do an example. Example 1, evaluate the inverse of sine at the square root of 3 over 2. So in this case, what we want is we want to find some value as an output. Now what is that output going to be? It's going to be some angle theta. The angles are the input for sine. So that means it's going to be the output for the inverse sine. So when you see something like this, what you're really looking for is you're trying to find a value of theta so that sine of theta is equal to the square root of 3 over 2. So we want to figure out what theta is. So we want to find such a theta. In order to help us, it might be useful to draw a little unit circle. So let's draw a circle here, and we'll give it some x-axis and a y-axis like so. So what we're trying to do is we're trying to find a theta so that sine of theta is the square root of 3 over 2. Now on the unit circle, sine is the y-coordinate. So we want the y-coordinate to be square root of 3 over 2. Now that happens in two different places on the unit circle. So that happens right about here. So this one is the angle pi over 3. But it also happens right over here. So this angle is 2 pi over 3. So the coordinates for this point here for the angle pi over 3, that's 1/2 comma the square root of 3 over 2. And this one over here is minus 1/2 square root of 3 over 2. So both of these values of theta will give us a sine of theta, which is square root of 3 over 2. And in fact, there are infinitely many more because I can keep going around the circle finding coterminal angles with pi over 3 and also 2 pi over 3. However, this sine of theta, this sine is on a restricted domain. So when we say find theta, we want to find theta on the restricted domain. So on the domain from minus pi over 2 to positive pi over 2. Minus pi over 2 to positive pi over 2. These are our allowable angles. So we have to choose an angle from that set. Now in terms of the unit circle, that's over here. Minus pi over 2 means a clockwise rotation by 90 degrees. So that puts you right here on the negative y-axis. Positive pi over 2 is the positive y-axis. So that means our angles have to come from this region of the unit circle. You can see that 2 pi over 3 is outside of that region. So what does that tell us? That tells us that theta must be pi over 3. So that's our answer. So sine inverse of the square root of 3 over 2 is pi over 3. And that's our first example. Let's try another one. The inverse cosine of minus 1/2. So again, the idea here is that this is going to give us some angle. Cosine inverse of minus 1/2 is going to be equal to an angle. And what is that angle? It's the angle theta, so that cosine of theta gives us minus 1/2. And again, we want to figure out what that theta is. So in order to help us, we draw a unit circle again. We draw a little circle and we give it an x-axis and a y-axis, like so. All right. There we go. Now what we're interested in is we're interested in angles where cosine of theta is minus 1/2. Now cosine is the x-axis, so that means we're going to be over here somewhere. We want to have a negative 1/2, so that's going to be right about there. So that intersects the circle in two places, so here and here. So these coordinates are minus 1/2 square root of 3 over 2, and down here in the third quadrant we have both of them negative, minus 1/2 minus square root of 3 over 2. Now the angles that get us here, so for the first one here, this angle is 2 pi over 3. This angle here, which is pi, that's 3 pi over 3. So 2 pi over 3, 3 pi over 3, this is 4 pi over 3. So this one is 4 pi over 3. And again, any angle which is coterminal with these two angles will also give us an angle theta, so that cosine of theta is minus 1/2. But once again, we're looking at a restricted domain for cosine. So the domain here is the set from 0 to pi. In terms of the unit circle, that means we're looking at angles on the top half. Pi is 180 degrees, so these are positive angles, so we're looking at a counterclockwise rotation between 0 and pi. So it's going to be the top half. That means we exclude this angle 4 pi over 3 because that's outside of the allowable range. So the answer is 2 pi over 3. So theta is equal to 2 pi over 3. And that's our answer. For our next example, we're asked to compute the inverse sine of cosine of 5 pi over 3. Well, the first thing we can do is figure out what cosine of 5 pi over 3 is. That's cosine evaluated at an angle, 5 pi over 3, so we can figure that out using the unit circle. So let's draw a circle, and let's draw an x-axis and a y-axis. Okay, where is 5 pi over 3 on this thing? So 1 pi over 3 is here, 2 pi, 3 pi, 4 pi, 5 pi. So 5 pi is down here. So 5 pi looks something like that. So this angle right here, that's 5 pi over 3. So this coordinate here will have x coordinate 1/2 and y coordinate minus the square root of 3 over 2. Well, we're interested in cosine of 5 pi over 3, so that's going to be the x coordinate, so it's going to be 1/2. So this is going to be 1/2. So what we're actually trying to find is sine inverse of 1/2. This is going to be equal to some angle theta. So the way we figure out what that theta is we ask ourselves, sine of what theta is going to give us 1/2? So we want sine of theta to be 1/2. So now we're looking at the y-coordinate. We want the y-coordinate to be 1/2. So 1/2 is right about there. So that's going to give us 2 points on the circle. We have a point in the first quadrant and a point in the second quadrant. In the first quadrant, well, let me just change the color of my pen here. So in the first quadrant, the point that we have has coordinates 1/2, not 1/2, rather, because that's the y-coordinate is 1/2. So this is 1/2. So the x-coordinate is the square root of 3 over 2, and the y-coordinate is 1/2. That angle is pi over 6. In the second quadrant, we have this point, and that has y-coordinate 1/2. So it's minus the square root of 3 over 2, comma 1/2. And this angle, notice that this has reference angle pi over 6. The angle is 5 pi over 6, because this is 6 pi over 6. 6 pi over 6 is pi. Since the reference angle is pi over 6, then 6 pi over 6 minus 1 pi over 6 is 5 pi over 6. Anyway, our objective is to find an angle theta so that sine of theta is equal to 1/2. That means so the y-coordinate is 1/2. Both of these will do that because they both have y-coordinate 1/2. And again, any angle which is coterminal with these two will work as well. But we're looking at sine on a restricted angle. This inverse sine is defined to be the inverse on a restricted domain for sine. So the domain for this sine is minus pi over 2 to positive pi over 2. So again, in terms of the unit circle, we're looking at angles on the right side of the unit circle. So in particular, 5 pi over 6 is outside of the allowable region. That means that the angle we're looking for is pi over 6. So in that case, theta is equal to pi over 6. And that's our answer. So we could write it all out. Sine inverse of cosine of 5 pi over 3 is equal to pi over 6. And that's our answer. Let's do another example. Here we want to evaluate the inverse cosine of sine of 9 pi over 4. So this is the same kind of problem that we did before. So the first thing we want to do is figure out what that value is. What is sine of 9 pi over 4? And again, in order to do that, we're going to make use of a unit circle. Okay, so let me just make that y-axis a little bit straighter. There we go. All right, so 9 pi over 4, that is greater than 2 pi, so that's more than once around the circle. So 9 pi over 4 is equal to 8 pi over 4 plus 1 pi over 4. So that's 2 pi plus pi over 4. So that means we start along the positive x-axis and we actually go all the way around, and then we keep going until we get to the angle pi over 4, which is roughly right, so let's say about that. So this is the angle pi over 4. Now, that's the angle we're actually looking at, pi over 4. Now, the angle in question, 9 pi over 4, is coterminal with this. So That's all the way around and back, like so. That's 9 pi over 4. But that's coterminal with pi over 4, so that's our reference angle. And it's in the same quadrant, it's in the first quadrant. So we can just use pi over 4. So sine of 9 pi over 4 is equal to sine of 1 pi over 4, and that's equal to square root of 2 over 2. That's because the coordinates of this point here are square root of 2 over 2, comma, square root of 2 over 2. So if the angle is pi over 4, then sine and cosine are both the square root of 2 over 2. So what we were asked to compute was cosine inverse of sine of 9 pi over 4. But we found that sine of 9 pi over 4 was equal to the square root of 2 over 2. So what we're trying to compute then is cosine inverse of sine of pi over 4. But we saw that this was equal to the square root of 2 over 2. So we want to find cosine inverse of square root of 2 over 2. Now this is going to be equal to some angle theta that we need to determine. Now theta is an angle such that cosine of theta is equal to the square root of 2 over 2. So that means we're looking for an angle theta on the unit circle so that the x-coordinate is the square root of 2 over 2. Well, we've already found one right here. If theta is equal to pi over 4, then the x-coordinate is square root of 2 over 2. There's another one, of course, because we're looking at the x-coordinate, which is square root of 2 over 2, and there's another one down here. This one, too. This one has x-coordinate square root of 2 over 2, and y-coordinate minus the square root of 2 over 2. So this one is, well, what is this one? This is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi, 6 pi, 7 pi over 4. So this one is 7 pi over 4. It's probably easier to think of it in the other direction because this is minus pi over 4. So if that's minus pi over 4, then 2 pi, which is 8 pi over 4, minus 1 pi over 4 will give you 7 pi over 4. However, we're looking at cosine on a restricted domain. So the restricted domain here for cosine is 0 to pi. On the unit circle, that's the top half. The top half includes the angles from 0 to pi, 0 to pi. So our restricted domain for cosine is 0 to pi. So in particular, 7 pi over 4 is outside of that allowable range. So in that case, we pick pi over 4. So theta is equal to pi over 4, and that's our answer. Let's look at a similar example. Notice that this is basically the same example, but we've replaced inverse cosine with inverse sine. You have to be a little bit careful with a problem like this because you might look at this and say, oh, well, inverse sine will cancel out with sine and just give me 9 pi over 4. However, that would be a mistake because sine inverse is the inverse of sine, but on a restricted domain. This angle, 9 pi over 4, is outside of that restricted domain. So sine inverse is the inverse of sine on the interval, on the restricted interval, minus pi over 2 to positive pi over 2. And this angle is outside of that interval. So let's just remind ourselves what it is by drawing a unit circle. That one's a little bit bigger than before, but I guess that's okay. So remember what it was. 9 pi over 4 was coterminal with pi over 4. So 9 pi over 4 was all the way around like that, and it was coterminal with the angle pi over 4. So sine inverse of sine 9 pi over 4 is equal to sine inverse of sine of 1 pi over 4. Now this angle is inside the restricted domain. The restricted domain for sine is the right side of the circle in terms of the angles. So the restricted domain for sine includes angles from minus pi over 2 to positive pi over 2. So this angle is minus pi over 2, and this one's positive pi over 2. So 9 pi over 4 is too big. It's outside of that range. However, it's coterminal with pi over 4, which is inside of that range. So sine inverse is the inverse of sine on an interval that contains pi over 4. So this actually is pi over 4. This leads us to a remark. The inverse trigonometric functions are only inverses of the trigonometric functions on the restricted domains. So sine inverse of sine of x is equal to x only if x is between minus pi over 2 and positive pi over 2. Similarly, inverse of cosine of x will give you x only if x comes from that interval from 0 to pi. And inverse tangent of x is equal to x only if x is strictly between minus pi over 2 and positive pi over 2. If x is outside of this range, then you need to find the x which is coterminal that is inside of this range in order to use these cancellation laws. Because again, the inverse trigonometric functions are inverses, but only on restricted domains. Let's look at another example. On the face of it, this might seem similar to the ones that we've done before, but it's actually quite different. The previous examples had the inverse function on the outside. Now the inverse function is on the inside. So what we want to do is we want to compute cosine of inverse sine of 3 over 5. Now the inverse sine is going to give you an angle. So this value right here is going to be some angle. So what we want to do is we want to compute cosine of theta, where theta is equal to sine inverse of 3/5. That's our objective. What does this mean? This means that sine of theta is equal to 3 over 5. We want to compute cosine of theta, and we now know sine of theta, so we can do that using the Pythagorean identity. So the Pythagorean identity tells us that cosine of theta squared plus sine of theta squared is equal to 1. So cosine of theta squared is equal to 1 minus sine of theta squared. So now we compute the square root. Cosine of theta is plus or minus the square root of 1 minus sine theta squared. This leads us to a temporary obstacle because we have plus or minus, but we need to figure out which one it is. Is it plus or is it minus? In order to know that, we need to know what quadrant we're in. We know that sine of theta is equal to 3/5. That means it's positive. So if we draw a unit circle, and usually to solve these problems, you're going to want to try to draw a unit circle. There we go. So we have a unit circle, and we know that sine of theta is a positive number. So what does that tell us? That tells us that sine of theta, which is the y-coordinate, is positive. So that means we're on the top half of the circle. If we're on the top half of the circle, then you might have a cosine which is positive here, or you might have a cosine which is negative over here. However, sine inverse is the inverse of sine on a restricted domain. So this function sine, the domain is restricted. So the domain is the set from minus pi over 2 to positive pi over 2. But that's the right side of the circle. So that means we have to look only at the right side of the circle. we're in either the first or the second quadrant, but we're not allowed to be in the second quadrant because the domain of sine is restricted to either quadrant 1 or quadrant 4. So we know that we're either in 1 or 2, but we can't be in 2. We can only be in 1 or 4, so that means we must be in the first quadrant. So that means that cosine is positive and sine is positive. So that means we choose the positive cosine. Cosine of theta is positive, greater than or equal to 0. So we choose the positive cosine, the positive square root. Therefore, we can say that cosine of theta is equal to the positive square root of 1 minus sine of theta squared. However, sine of theta, we know what sine of theta is. Sine of theta is 3/5. So this is 3/5 squared. Sine of theta is 3/5. So that means cosine of theta is equal to the square root of 1 minus 9 over 25, which is the square root of 16 over 25, which is 4 over 5. So cosine of theta is 4 over 5. And that's what we were trying to compute. We wanted to find cosine of this angle theta. Theta was the inverse sine of 3/5. So we wanted to find cosine of theta, and we've just done that. Now another way to do this would be to construct a right triangle. We know that sine of theta is 3/5. So we could construct a right triangle with those dimensions. So let me just erase where I went a little too long there. Okay. So if this is our angle theta, we know that sine of theta is 3/5. So sine of theta, well, what is sine? Sine is the opposite over the hypotenuse. But we know that sine of theta is 3/5. So this is equal to 3/5. So we can construct a right triangle with these dimensions. So the opposite side is 3 and the hypotenuse is 5. So we have a right triangle with opposite side 3 and hypotenuse 5, so you can again use the Pythagorean identity to show that this side is 4, because 3 squared plus 4 squared is equal to 5 squared. So then what does that tell you? That tells you that cosine of theta is equal to, well, it's equal to the adjacent over the hypotenuse, which is 4 over 5, which is the same answer. Now you still have to know whether you're looking at a positive or negative value, but it's going to be positive for the same reason that we saw here. And in fact, on the restricted domain for sine, you'll notice that the restricted domain is minus pi over 2 to positive pi over 2. That's the restricted domain for sine. But on this restricted domain, notice that cosine is always positive. So in the restricted domain for sine, cosine is always positive. Similarly, on the restricted domain for cosine, sine is always positive. And we can see that in our next example. Here we're looking at sine of inverse cosine of 2/3. And so we're going to do this the same sort of way. We begin by saying that cosine inverse of 2/3 is going to be some angle theta. So we want to determine sine of theta. We want to figure out what this is, where theta is equal to cosine inverse of 2/3. Well, if theta is cosine inverse of 2/3, that means cosine of theta is equal to 2/3. So we know what cosine of theta is, and we want to find sine of theta. So once again, we can use the Pythagorean identity. So we know that cosine of theta quantity squared plus sine of theta quantity squared is equal to 1. So now we're trying to find sine of theta, so we solve for that. So we subtract cosine of theta squared from both sides. We have sine of theta quantity squared is 1 minus cosine of theta squared. And then we compute the square root. Sine of theta is equal to plus or minus the square root, let's try that again, square root of 1 minus cosine theta squared. And again, we have to determine if it's a positive or a negative square root, but it's just like before. We draw a unit circle, like so, and we're trying to figure out where our angle is. Which quadrant are we in? Well, what do we know? We know that cosine of theta is 2/3. So cosine has to be some positive number, or cosine of theta has to be a positive number. So that means our x-coordinate on this unit circle is a positive number. So that means we're over here somewhere. So that means we're over here. However, we're looking at cosine inverse of 2/3. And cosine inverse is the inverse of cosine on a restricted domain. So this cosine of theta, it has a restricted domain. And its domain is the set from 0 to pi, or the interval from 0 to pi. And that's the top half of the circle. So again, we're looking at something that's either in quadrant 1 or 4, but it has to be in quadrants 1 or 2. So the only way that can happen is if it's in the first quadrant, where they're both positive. So that means that, in particular, sine of theta is going to be positive. So we're choosing the positive square root. So sine of theta is equal to the positive square root of 1 minus cosine theta squared. And it has to be the positive square root, because notice on this restricted domain for cosine, sine is always positive. So sine has to be positive. Now we solve for sine, or sine of theta. We know that cosine of theta is 2/3, so we just plug that in here. So cosine of theta is 2/3, so you just plug that in where there's a cosine theta. So sine of theta is equal to the square root of 1 minus 2/3 quantity squared. Sine of theta is the square root of 1 minus 4 over 9, which is the square root of 9 over 9 minus 4 over 9 is 5 over 9. So sine of theta is the square root of 5 divided by 3. And that's our answer. Let's do one more example. So here it's sine of cosine inverse of minus 2/3. So notice this is very similar. Sine of cosine inverse of 2/3, sine of cosine inverse of negative 2/3. So the only difference is now that we have a negative here. So how will that change the problem, if at all? So we do it the same way. This angle is going to be theta. So we want to find sine of theta. What is that, given that theta is equal to cosine inverse of negative 2/3? So that means cosine of theta is equal to negative 2/3. So we need to know whether sine is going to be positive or negative. We need to figure out what quadrant we're in. Oops, that's a terrible unit circle. Let's try that. There we go. Now again, we know that cosine of theta is a negative 2/3. So that means that the x-coordinate is negative. So that means we're over here somewhere. However, the domain for cosine, again, just like before, this domain is a restricted domain, 0 to pi. So that's the top half of the circle. So that means we're in the second quadrant, where now x is negative, cosine is negative, but sine is the y-coordinate, that's positive. So on the restricted domain for cosine, sine is always positive. So that means when we compute the square root, we use the positive square root. Cosine of theta squared plus sine of theta squared is equal to 1. So sine of theta squared is equal to 1 minus cosine theta squared. So sine of theta is equal to plus or minus the square root of 1 minus cosine theta squared. But again, sine is positive, so that means we're going to select the positive square root. So sine of theta is the positive square root of 1 minus cosine theta squared. From here on out, the calculations are essentially the same, because we have sine of theta is equal to the square root of 1 minus cosine of theta squared. But what is cosine of theta? Cosine of theta is minus pi, not minus pi, minus 2 over 3. Minus 2 over 3. So sine of theta is equal to the square root of 1 minus, well, negative 2/3 squared is still 4/9. So now we have the square root of 1 minus 4/9, which is the square root of 5/9. So sine of theta is the square root of 5 divided by 3, just like before. And that's our answer.